So today's warm-up questions, the number 1 says which periodic table elements are ferromagnetic, and number 2 says true or false, cutting a magnet in half can give you one magnet that is just a north pole and a second magnet that is just a south pole. Okay, so let's talk about these because these questions were answered in our notes last week. So the ferromagnetic is just asking about what those elements are that make up our permanent magnets, or what the elements are that make up materials that would be attracted to those permanent magnets. And there were only 3 that we talked about: iron, cobalt, and nickel. Okay, and so you should have, those are your ferromagnetic elements. You should make sure that you have that written down for your warm-up question as well, and it should definitely be in your notes. Okay, but those are your ferromagnetic elements: iron, cobalt, and nickel. The second question, cutting a magnet in half gives you two monopoles, okay? One magnet that's just north, one magnet that's just south. That's the second question, true or false? Okay, that is false. I mentioned this before, but if you were to cut a magnet in half, and again, this is another way that I could ask that question, okay, what would the resulting pieces look like? And it would not be D, okay? You would not get just a north and just a south. That's not possible. And the reason is because of this. Remember these domains that we talked about? If I cut this magnet in half, I still have a front end and a back end, if you will, to each half. The arrows are still all pointing that same direction. So we still have something that looks like this if it's cut in half, which means we still have a north and a south pole on each of those halves of the magnet. So if you cut a magnet in half, you simply get 2 smaller magnets. Okay. I also want to mention this because I've labeled north and south on here, and you might be thinking, but Ms. Darwin, whenever we drew our magnetic field lines, you said to draw them from north to south. Why did you put the labels like you did? Okay, and that is because when we draw those field lines around the magnet, it does go from north to south. But you have to close the loop inside the magnet as well, and within the magnet, inside of it, it looks like this. Okay, if you were to actually connect those same field lines that we were drawing. And again, you saw this in one of the questions that you had in your assignment from last week, where the field lines were actually drawn inside the magnetic material as well. And it does look like this. Okay, so inside the magnet, it would look like this. But around the magnet, if I were to draw field lines, I would have them drawn from north, looping around to south like this, but then they go through the material as well. Okay, so just to clear that up in case there were any questions there, but the answer to number 2 is false. Okay, if you cut a magnet in half, you do not separate the north and south poles. Instead, you get 2 smaller magnets. All right. So like I said, we do have some notes today. So you should have paper out. If not, go ahead and get some paper out. If you got a phone out, let's go ahead and make sure those are put away. That way we can all pay attention to what's going on. So we're going to start with some stuff that's a little bit of a recap of what we were talking about last week. Directionality of the magnetic field. We've already discussed this, but your magnetic field is a representation of magnetic forces in a region. Those field lines show you the direction that something would be pushed or pulled based on its magnetic characteristic, whether it's a north pole or a south pole. Okay, and so that magnetic field, or those field lines, describe how the magnetic force is distributed in the space around and within something magnetic, and they always point from north to south when drawn around your magnet. Again, if I asked you to draw magnetic field lines around a bar magnet that looks like this, you should be able to draw something with those field lines drawn from north to south like this. Okay, so from north to south in these loops going, and now of course if you continued the line through the magnet, you could, because technically you should. You could also show it inside that material, and they would continue and close those loops. But that's something that you should be able to draw, or if I give you a picture with the field lines drawn and say which of these is the North Pole, you should be able to tell me that. Okay, lots of different things we can ask you about field lines, drawing them in, or just using them to identify something or to answer some question about that magnet. Okay, so again, reviewing some of the stuff we talked about last week. So if I asked you to draw the field lines here, again, take a second, and you can even draw this on your paper, but I have the north pole of one magnet and the north pole of another magnet. Now again, each of these does have a south pole. We can't separate the two. It's just not in my picture. They'd be off the screen over here to the left and over here to the right. But I'm going to ask you to just draw the interaction between these two north poles. So I'm going to give you a second. Draw it on your paper. You can turn and talk to your neighbor if you're not sure. But take the next 31 seconds to see if you can sketch out something that shows the interaction between two north magnetic poles.
What do they just call it? Like?
Yes.
Yeah.
All right, so should these attract or repel? Let's start there. Repel, yeah, good job, Emily. Okay, they should repel. And so if you're drawing them in, you should see that repulsion. Those field lines should kind of curve away from each other, like as they go toward each other, but then they, go up or down in that space, leaving kind of a void here. And because we draw our field lines from north to south, you'll notice I also have those arrowheads pointing in the appropriate direction because they should be pointing away from my north poles, and that is the direction that we have drawn them here. So your picture should look something like this. Okay, again, it doesn't have to be exact, but something like this. You can add that to your notes if you didn't already draw it. All right, so again, other questions we could ask you. Which compass needle orientation in the image correctly describes the magnet's field at that point? This is just like the warm-up question from yesterday, just a different picture. So take a second, and again, you might have to sketch the field lines in to see which one would be correct. But take a second and see if you can figure out which one would be correct, A, B, C, or D. You can talk to your neighbor if you're not sure. And then we'll discuss this when my timer goes off in 25 seconds.
Please pardon this interruption. Good morning. This is a quick reminder.
All right, guys, so again, your field lines around your magnet point from north to south. So which of these would show a correct compass needle at that position, A, B, C, or D? What did you say, Braden? D. Yeah, if you draw in those loops, okay, that point D is what you would expect to see as you get closer to that south pole. I thought I had them in here. But again, if you go from north to south, A and C are pretty much backwards from what I would expect. B doesn't make any sense. But if you think of that loop going from north over here to south, it would curve back into the south pole, so you would expect it to be at a diagonal there. It would fall along that field line. You can see similar field lines here. Again, as they approach, you have this diagonal line coming in. Okay, at which point is it the strongest? I think I've actually given you this exact picture before, but you can tell the strength of your magnetic field by the density of your field lines. In other words, where are the lines closest together? And that, of course, in this image would be at point C. And so we would have the strongest field at point C because my field lines at point C are closest together. That's always going to be strongest at the poles. So if you're at the very end of the magnet, like right next to it, your field lines are closest together there. And that's true on both sides, both the north and south pole of this magnet. The field lines are closest together. All right. So we also looked at the fact that you can see a magnetic field form around a current carrying wire. And we saw this in one of the simulations from last week. But when you ran that current through a wire and you moved the compass around the wire, your compass needles pointed in a circle. So in front of the wire, you saw something that looked like this. Okay, behind the wire, it's in the opposite direction. We also saw this in the RA that we did in the last unit. Whenever we had the compass below the wire and then on top of the wire, you saw the same thing. Your compass needle deflection went in the opposite direction. I don't know if you remember that or not. It's been a little bit of time since then. But you get a magnetic field that you can see with these compass needles as you move them in three-dimensional space around that wire. Okay, or if you just set them at these positions around the wire, they would look like this when you turn on or run the current through that wire. And we're going to talk a little bit more about this three-dimensional aspect of this field today and how we can represent that, because it's kind of tricky to see. I mean, this arrow, I know that I'm trying to draw it with perspective, so I know I'm drawing it, meaning that I'm going into my screen as opposed to up. But again, without that knowledge that we're trying to do it with perspective, it can be kind of tricky because it is literally an arrow pointing up. Okay, and so we're going to talk about some symbols that we can use that allow us to represent this three-dimensional aspect of our field and show when something's going into our screen or out of our screen versus up or down. Okay, and again, this is the part of this unit that is the trickiest, is the three-dimensionality of it. So again, please make sure that you're listening, because the hardest part of the magnetism unit is what we're about to do. Okay, and so we need to be able to represent directions other than up, down, left, and right that fall along the plane of our paper or the plane of this screen. We need to be able to show also things going into the screen or into the page we're looking at, or out of the screen at us, or out of the page that we're looking at if it's on paper. Okay, and so we have some symbols that allow us to do that. Okay, obviously we can use arrows up, down, left, right, that's fine. But if you want to show something that is going into the page, the symbol that we use looks like this. And again, you're going to want to put this in your notes. Okay, so the symbol that we use for something going into the page is an X inside of a circle. The symbol that we use for something coming out of the page or out of the screen is a dot inside of a circle. I'm going to give you a trick to remember it, but copy them down. Symbols, okay, and here is what we use to remember them. Okay, if you think of archery or even a dart, okay, this is basically a giant dart. But if you look at the back of it, if it's fired away from you, you are literally looking at something, the fletching on the back looks like an X. Okay, and so if it's moving away from me, meaning like if it's going into my screen away from my face, I'm going to use this symbol to show that it's moving away from me, like I'm looking at the back, the fletching on the back of my arrow. If it's coming toward me, I'm going to see the point at the tip of this. So if it's coming at you, out of the screen at your face, you're going to look at that dot. Okay, at your face. Okay, so those are how I remember the symbols. If you find that to be helpful, use it. Okay, but again, you can use an arrow or a dart to remember the symbols, because you can see the back of this would look like an X as it's moving away from you. So if it's going away from my face into the screen, I'm going to use that X. If it's coming out of the screen at my face, I'm looking at the tip, okay, the dot. Okay, so if we wanted to represent the field on either side of this wire, rather than using an up arrow and a down arrow and trying to show it with perspective, we're going to use these symbols. Okay, and so this one here that's to the left side of my wire, so this one, instead of a down arrow, it's coming out of the screen at my face. Okay, and if it's coming out of the screen at my face, it's like the arrow flying at my face. I'm going to be looking at the dot. Okay, and so I have a dot over here. On this side, instead of drawing an up arrow and trying to show it going into my screen, again, if it's going into my screen, I'm looking at the back of it. It looks like the X, and so we're going to use that symbol instead. Okay, so again, showing the same thing, but using three-dimensional symbols instead. Okay, so that brings us to the right-hand rule, and technically it's right-hand rules because there are two of these. Okay, this is the tricky part, is because, you saw in the video clip that I showed you of the guy running the jumper cable wire through the magnets, he actually did the right-hand rule. And he talked about the fact that he was doing the right-hand rule, but now I'm going to teach it to you so that you can do the same thing. The right-hand rule allows you to take a look at a scenario or an experimental setup if you actually were to take magnets and a wire. Okay, but it allows you to take a look at a question or a physical setup, and it allows you to determine what direction your field will be or what direction the current has to be running based on the field or the direction of the force applied to a current carrying wire. And that's the one he was talking about in his video clip. He said the force is going up, the wire is going to jump. Okay, and so whenever we do the right hand rule, first of all, it is called the right hand rule. It's not called the left hand rule, so please make sure that you use your right hand. And you will be actually using your hand for this, and you are going to look kind of goofy. Okay, I'm just warning you right now. But there are two of these rules. So the first rule, the one that's on the left-hand side of my screen, will show us the direction of the magnetic field due to a current carrying wire. So when the wire has current flowing through it, a field is formed around the wire, and we pretend that we're wrapping our fingers around that wire, just like you see in that picture. And when we do this, we're going to point our thumb in the direction of the current, and our fingertips are going to represent the direction of the magnetic field that's formed around it. Which means if our current's flowing the opposite direction, we turn our hand, our field is now also going in the opposite direction. Okay, the second right-hand rule describes the force that would act on a current carrying wire that is flowing through an existing magnetic field. Okay, because now we have two magnetic fields. The wire itself makes a field, but then it interacts with the other field. And so it shows the force that is the result of that. And so this one you'll use if you have physical magnets on the page with a wire running through them. Okay, or if you have a magnetic field physically labeled on the page with a wire running through it. And so the right-hand rule number 2 shows us the direction of force on a positive, on a moving positive charge through a field. Again, we always do this for conventional current. Conventional current meant that we had moving positive charges. So if I show you a question and it shows a moving electron, everything's going to be backwards. Okay, you're going to get your answer and then you're going to give me the opposite answer because this is all defined based on conventional current. Okay, for the second right-hand rule, you're going to leave your hand flat. The current is still represented by your thumb, just like it was in this one. My thumb is still the current. My fingertips are still the magnetic field, just like it was in the first one. The difference is that now I'm holding my hand flat and I have a third thing to consider, and that is the force is going to come straight out of my palm, like if I was to slap somebody with my hand. Okay, that's the direction that I'm pushing. Don't actually slap your neighbor in the face, though. Okay, but you can see it, again, trying to represent it here. But it's going to take some practice. All of these, by the way, are at right angles to each other. They are my X, Y, and Z axes. Okay, so I have a right angle here, because this is going this way, this is going up, and then the other one's coming out this way. So it's X, Y, and Z, three-dimensional space. All right, so let's try some examples. Okay, this one says, indicate the direction of the magnetic field around the current carrying wire. I have 3 wires here. I'm going to start with this image. Okay, but if I'm looking at the direction of the field generated around a wire, I have 2 rules. The one I'm going to use is the first right-hand rule. I'm not looking for force. Okay, I'm not looking for that. So I'm going to use this one, okay, where I curl my fingers. And to do that, let me do it on my screen here. I redrew these. Okay, to do that here, I'm going to, first of all, this is my right hand. Okay, I'm going to put my thumb in the direction of my current. Okay, so it's going to point up. And when I do that and I curl my fingers around, it's going to look like this. And again, you can literally grip something. That's my wire. So my current is going up, and when I do that, my field is going in on this side and it's coming out on this side. Okay, so my field comes out over here and goes in over here. Okay, out, in. And again, we talked about symbols for that. Bless you. Okay, so if I wanted to show that coming out over here, it means I'm looking at the tip of the arrow. It's coming at me. Going in over here means I'm looking at the back of the arrow. Again, that's what I saw. It goes in and then comes back out. Look at my fingertips. In, behind, out. Okay, and so I would label this as my field. And it's going to be different on either side of the wire because it's in a circle around the wire. Again, if you literally hold something, you can see that. It would form a circle around this pencil if my pencil was my wire. Okay, and I could draw more of these symbols, but it'd be different on either side of the wire. This one, now I need to show my current going away from me. That's the back of the arrow, which means it's going into my paper. So I'm going to turn my hand so that my thumb is going into the page. And when I do that and I curl my fingers, okay, they are going to go in this direction. Again, try it yourself. They're going to go in that direction. Okay, thumb's going in, that's my current. My field goes like this, so it is in a clockwise direction. Whereas this one, my thumb needs to come out. And I curl my fingers around, and look, it's the exact opposite direction. It's going to go this way in a counterclockwise direction. So let's go back here real quick. Okay, again, we use those symbols here, out and in. Over here, we said it's going to go clockwise. Here, it's going to go counterclockwise. Does anybody have a question so far about our diagrams? Okay, so this would be my field. I could label it with a B. All right, let's try another one. This one shows a field that is the same on both sides of the wire. If you read the question, it says, indicate the direction of the force exerted on the current carrying wire traveling through the magnetic field. This time the field isn't made by the wire. Now the wire still technically makes one, but if it's flowing through a magnetic field because there's magnets, that is a much stronger field. So that's the one we're going to see. Okay, so this is an example where I have a magnetic field, I have a wire going through it. Think of the video with the jumper cable going through the horseshoe magnet. Okay, so that's why this is the same on both sides. And if you ever see force, you're going to use the second right-hand rule. Okay, or if your field is the same on both sides of the wire, you're going to use the second right-hand rule. So you need to keep your hand flat this time. And you need to, your fingertips again are B. Okay, so let me bring this over here again. Your fingertips are going to be B. I'm doing this one. It's the same picture. And so my fingertips, I need to have them going into my page. I'm looking at the back of the arrow. It's going away from me. So I'm going to put my fingertips into the page. Okay, right now, when I do that, my thumb is going the opposite direction that it needs to. So I actually need to turn my hand like this. My fingertips are into the page. My thumb is in the direction of the current. When I do that, my palm is pointing along my paper. It's pointing up. Okay, again, I'll do it in front of the screen also. Actually, I do this. Fingertips into the page, current going this way. When I do that, my palm is pointing up. Okay, so that is the direction of my force, is upward. And you're going to have to practice this, okay? It's kind of weird. And you are actually going to need to move your hand in these kind of weird ways. Yes? It doesn't have to be. I mean, you could be looking at this screen right here. My current is, or my field is going into that screen. You don't have to be looking down from above. All right, that's my force. Okay, one thing I want to mention, guys, I, when you see I up there, that is conventional current flow. So as a reminder, it could look like this. Some of the ones are going to say, here's a positive charge going this way. That's the same thing as conventional current. Conventional current is the flow of those positive charges. We talked about this in the last unit. So if you see a positive charge with its velocity labeled, that's your thumb. That's your current. However, if you see a negative charge with the velocity labeled, okay, then that's exactly the opposite direction. So you can either do this like normal, okay, and say, okay, my fingertips are going in, my thumb's this way, but it's an electron, so instead of up, it's down. You can do that. Or you can point your thumb in the opposite direction. We're going to get to one example later on in these notes that has an electron, the electron flow labeled instead. Okay, and I think you have one like that in your practice today. So just a heads up. All right, this one says, indicate the direction of the current flow through the wire. Look at my picture. Which right-hand rule am I going to be using? 1, because I have a different field on either side of the wire, so I know that I'm dealing with something going around the wire. There's also no force label. Okay, so I'm going to use the first right-hand rule. And I need to do this so that my fingers go, let me switch it over to my document camera again. Oops. So that my fingertips go in, away from me here, and then back out like this. When I do that, which way is my thumb pointing? To the left. That's the direction of my current flow in this wire, because I need to go in and back out. Again, you can grip something and pretend it's a wire, okay, if you need to. But that is the direction of my current flow. It's going to be to the left. It's like this picture here as opposed to this one. This one's to the right, but that's going in underneath and out on top. That's backwards from what this shows. In on top, out on bottom is this picture right here. Okay. Let's try this one. Here I have a north and a south end of a magnet labeled. And my wire is flowing in between them. This is just like that horseshoe magnet. There was a north and a south with the wire flowing in between it. Okay? My magnetic field isn't labeled. However, you should know which way it's going to be. Which way does our magnetic field always go? From north to south. So you can add in your magnetic field. By the way, if the question's asking for the force exerted, I know it's the second rule. I'm going to keep my hand flat. Okay, my force exerted when my wire goes through a field. That's always going to be the second rule. So I added in my field, north to south, and then I'm going to hold my hand so that my fingertips point in the direction of my field, and my thumb points in the direction of the current. And when I do that, my palm is going into the screen. That is the direction of your force. Okay, I'll show you on here also. Okay, north to south is this way, thumb is up, palm is facing down into the paper. So if I wanted to sketch that force, it would look like this. Into the page is an X because I'm looking at the back of the fletching on the arrow as it goes away from me into my screen or into my page. Questions about that one? All right, here is another one. I told you that I was going to show you one with a negative charge. Here's my negative charge. This one says, if the moving charge is negative rather than positive, use the right-hand rule and give the opposite answer. You can do that, or you can point your thumb the opposite way and get the right. I don't care which way you do it, whichever way is easier for you. Okay, but in this case, again, I can add in my field. It's always north to south. Okay, and now this is the direction of my electron flow. It's not my conventional current. It's exactly backwards from my conventional current. Okay, so let me go ahead and bring my document camera back up. That's this one. North to south is this way. And now my thumb, normally if I went into the page, okay, it looked like this, but that would be for conventional current. So if I wanted to do it for electron, I can either flip my hand and say it's down, or when I do it this way, I could say, well, conventional current would be a force up, so electron's down. I don't really care which way you choose to do it. But my fingers are going to go north to south, and then my current, remember this rule is for conventional. So if this is into the page for electrons, that means conventional would be out of the page. And I'm going to get a force that is downward. Whichever way makes the most sense to you is what you should do for these types of things, but be careful if it's an electron, because that means it's going to be backwards from what you normally would get. Questions about that one? Really have to practice this on your own. So this assignment for today, 1202.2, right-hand rule problem set. Do that right now. Okay, do as much of it as you can while you're in here. That way if you do get stuck on something, you can help each other or you can ask for help from me, because you do have to physically practice this. It is not something that's necessarily common sense. It's really awkward. Sometimes it might be easier to turn your computer screen. So if you find yourself trying to twist your arm in a really weird way, maybe try to rotate your computer instead. Okay, this is due by 11:59 p.m. tonight. If you have questions as you're working, please let me know.